Divisibility is a key concept in number theory, so we'll be spending a lot of time on it. In the meantime, a key idea to keep in mind. Avoid division. Also, definitions are the whole of mathematics, all else is commentary. So let's remind ourselves what the definition of divisibility is, and we note that we also say that if A divides B, then A is a divisor of B. So let's find a few quick theorems. Since for any whole number n is n times 1, then n divides n. And since n is also 1 times n, then 1 divides n. What about 0? As a fundamental rule, you can never divide by 0. This also means that 0 should never be considered a divisor. On the other hand, since 0 is any number times 0, then any number is a divisor of 0. Now, with some more effort, in another class really, we can also prove a useful theorem. If A divides B, then A has to be somewhere between 1 and B, where we use the absolute value because in principle number theory actually concerns the properties of the integers, and so A and B could potentially be negative. Now, one important idea. Suppose A and B are integers. There may be several common divisors. Now, a useful guide in math and life, look for the greatest and the least. So we could consider the least common divisor. But since all integers are divisible by 1, then any pair of integers has least common divisor 1. And a question whose answer is always the same is usually uninteresting. So our common divisors include 1 and maybe some others, and this suggests we might look for the greatest common divisor, traditionally written this way, which is the largest integer that divides both A and B. Now, this notation looks a little too much like a lot of other things, so we'll use the notation GCD AB. This also reminds us that the greatest common divisor is a function of the values of A and B. Now, the naive method of finding the greatest common divisor: list all divisors of both numbers, find the greatest divisor. Now, we'll sometimes use this phrase naive method or naive approach, and this really doesn't mean anything other than it's the obvious method for solving the problem, not necessarily the best. So we might want to find the greatest common divisor of 36 and 60, so I'll find the divisors of 36, which are, and the divisors of 60, which are, and we note that there's several common divisors, and the greatest of these is 12, and so that's our greatest common divisor. So one of the traditional roles of a number theory course is training people to think like mathematicians. So let's consider some mathematical approaches to problems. The first thing to keep in mind is just because you've defined something doesn't mean it has to exist. And that means that we often spend time in mathematics proving existence and uniqueness. Suppose we want to find the greatest common divisor of two numbers. If it doesn't exist, we could waste a lot of time looking for it. So let's prove that it exists. We'll go into some detail in order to introduce some proof techniques that we'll find useful. So a useful strategy in higher mathematics: start with a set and prove it's non-empty. So let D be a set of integers that divides both P and Q. Now we know that 1 divides P and 1 divides Q, so D is not empty. It contains at least 1. And since D is non-empty, then there's a greatest element, which will be the greatest common divisor. Or is there? It's conceivable that D might be an infinite set with no greatest element. So we need to prove there is a greatest element in at least one of the sets. So suppose P is greater than Q. Remember, you can assume anything you want as long as you make it explicit, and one of these numbers has to be greater. Then P doesn't divide Q because it's greater. And similarly, if some number P prime is even greater than P, that number can't divide Q. So D can't include any elements P or more, because they won't divide the other number. Since D includes 1, but nothing equal to or greater than P, it must have a finite number of elements. And so it has a greatest element, and by construction, D divides P and D divides Q, so it will be the greatest common divisor. Our proof strategy is actually a general one. We define a set of integers, we show that the set is non-empty, and then we show that the set is finite. And this relies on the following idea that a finite, non-empty set of integers must have a least and greatest element. And in this case, we proved that if P and Q are integers, there's some integer D that is the greatest common divisor of the two. There's just one little problem. Mathematicians care about existence. We proved that a greatest common divisor exists. But almost everyone who uses mathematics cares about solutions. The greatest common divisor is guaranteed to exist, but how do we find it? Well, our naive solution seems to work well until you consider real problems like find the greatest common divisor of these two numbers. So how can we solve this problem? Well, let's investigate.